Okay, so today we're going to talk about vertical stretching of a graph. But before we start using any numbers or values or making any calculations or anything like that, let's just try to picture what it means to stretch a graph, to vertically stretch a graph. Let's just try to visualize what the graph is going to look like and what's going to happen to it. Now, let's just call this graph f of x to be consistent with the book. Now pretend that f of x is anchored at the three spots where it crosses the x-axis, which are also called zeros, because at those three spots the y value is 0. We'll talk a little bit later about why this graph is going to be anchored at those three spots, but right now let's just pretend that it just is for the sake of being anchored there. And then let's pretend we're going to stretch this graph. Let's pretend we grab it and physically stretch it at the maximum and at the minimum. Now what's going to happen if we do that? Make this blue. And we know that if we pull the maximum up, the maximum is going to be a little higher. If we pull the minimum down, the minimum is going to be a little lower. And since it's anchored at -2, 1, and 4, those points won't change. But everywhere it's not anchored, they will change. So every point along this graph between -2 and 1 will go up a little bit. And every point between 1 and 4 will go down a little bit. Now let's sketch that out a little bit. What does that look like? So because when you stretch it, graph tends to get a little narrower. We'll start just a little bit inside, goes through the 0 up to the new maximum, back down through the 0 to the new minimum, and back up through the 0 again. Make that a solid line to make sure it's easier to see. The 0, back up. Now we'll call this blue one g of x. And now g of x has been stretched. G of x is f of x, but it's been stretched. And you can see it looks a little narrower between this interval, between -2 and 1, because it went a little bit higher, but in the same amount of x space. Same thing over here. It's a little narrower on this side because it went a little bit lower, but in the same amount of the change of x. So that's what we mean by stretching a graph. We anchor it at the zeros, and everywhere else gets pulled either up or down. Now let's explore this a little bit more with actual values and see what we find. Now this is the same graph from before, so we'll call it f of x again. And now we want to look at the critical points of f of x. And by critical points, we're talking about x-intercepts, y-intercept, maximum, and minimum. So let's put some values to that. The three x-intercepts appear to be -2, 0, 1, 0, and 4, 0. The y-intercept appears to be, let's say, 0, 8. The maximum is about -0.810, and the minimum is about 2.810, -10, excuse me. And the book wants us to perform a transformation. We're going to stretch this graph, vertically stretch this graph. And how it wants us to do that, we're going to label it g of x, is to multiply f of x by 1.5. Now let's think about what it means to multiply f of x by 1.5. So the x represents your input value, or your x value, and then the f of x represents your output value, or your y value. And for our new graph, g of x, we're going to take our f of x output, or our f of x, and we're going to multiply it by 1.5. And this will hold true for all points on the graph, but we're going to look specifically at the critical points. So let's make a little table and see what this will look like. Make the table in red. Critical points. And of f of x and of g of x. And we want to see what happens at the minimum, at the maximum, at the y-intercept, and at the x-intercepts, which we will label the zeros. Again, it's the 0 because at those x values, the y value is 0. So we already labeled them for f of x. So the minimum is, go to black, 2.8 comma negative 10. The maximum is negative 0.8 comma positive 10. The y-intercept is 0 comma 8, and the zeros are at negative 2 comma 0, 1 comma 0, and 4 comma 0. Now let's do some calculations, and then we'll plot it and we'll see what g of x really looks like. So the minimum of g of x will be found by plugging in the x value at the critical points, determining what f of x will be, which is the output at the given input, and multiplying that output by 1.5. So let's determine the minimum. If we plug in 2.8 to x, the output is a negative 10. Multiplying negative 10 by 1.5 gets us negative 15. So the minimum is 2.8 negative 15. It's a little smashed. Let's do the same thing with the max. If we plug in 0.8, negative 0.8 into x, the value we get from f of x is 10. Multiply that by 1.5, we get negative 0.8, comma, positive 15. If we plug in 0 for x, the output we get is 8. We multiply that output by 1.5, we get 0, comma, 12. If we plug in negative 2 for x, the output we get is 0. If we multiply 0 by 1.5, we get 0. So that 0 stays the same. If we plug in 1 for x, the output we get, again, is 0. 1.5 times 0 is 0. That one stays the same. And similarly with the last one. And that is why we anchored the last graph at those 0 points, because they actually stay the same, since you're just multiplying the outputs, and the outputs at those points are 0, and anything times 0 is 0. So let's plot this graph. Start with the zeros. They're going to stay the same. So we have g of x, got a point at negative 2, 0, 1, 0, and 4, 0. And we know it has a minimum at 2.8, negative 15, which is right there. And it has a maximum at negative 0.8, 15, which is right there. And it now has a y-intercept at 0, 12, which is roughly somewhere in there. Now let's connect these dots. So we go up through the 0, through the max, through the y-intercept, through the 0, through the min, through the 0. Make this a solid line once again. And there we go. Oops. The blue line is now our g of x, plotted with actual values. As you can see, it's very similar to what we visualized it to be on the last slide, but this time it's actually got values associated with it. And just to recap, the way we find those values is we take the critical points, again the zeros, the y-intercept, the maximum and the minimum. We find what the output will be at the given input, or in other words, what the y value will be at that given x value, and then we multiply that y value by whatever scalar they want us to. In this case, the scalar is 1.5. And then we plot the new points on the graph, and we can get a rough sketch of what that graph will look like. Alright, now we want to do one more quick recap, and we want to be very general in this recap and come up with kind of an expression or an idea of what any kind of graph labeled f of x will look like if we stretch it. So let's create another table. Oops. And parts 1, 2, and 3 are all talking about the critical points that we discussed on the last two slides. So we'll label this critical point. And our critical points again are maximum, our minimum, our y-intercept, and our x-intercept, which we'll call 0. Our zeros, excuse me. And let's look at this in relation to what f of x will look like and what g of x will look like, where g of x equals k times f of x. So now let's examine our critical points and what values they will have. So just in general, our maximum at f of x is going to be x1, comma, f of x1. And I use the subscripts 1 just to differentiate these numbers from the other critical points. And the minimum, similarly, will be x2, comma, f of x2. The y-intercept is going to be 0, comma, f of 0. And the zeros, and there may be many zeros, no zeros, some zeros. Let's just, for the sake of argument, do a couple. Will be x4, comma, f of x4, which will be 0. And x5, comma, f of x5, which will be 0. Now similarly, let's look at g of x. Remembering back to the last slide where we multiplied f of x by 1.5 to get g of x, we're going to do the same thing. We're going, except for this time it's going to be in general. So we're going to find the output at a given input, or the y value at a given x value, and we're going to multiply that output by the scalar of k. So that will give us x1, comma, k times f of x1. The minimum will be x2, comma, k times f of x2. The y-intercept, and again I put 0 for this x because the y-intercept occurs when x equals 0, so it's always going to be 0, will be 0 times k times f of 0. And then these zeros, or the x-intercepts, since they have an output of 0, k times 0, whatever k is still going to be 0. So they're going to be the same, like we've mentioned in the last two slides. So we have x4, 0, and x5, 0. And there we go. I think we've talked quite a bit and had a pretty good discussion about the critical points in general of a graph and the way it looks when you vertically stretch a graph and compare it to the original graph.